here we are. We're going to start Chapter 9 here. Chapter 9 is about significance testing. So it's our next entry into doing inference on statistics. So again, it's taking sample data and inferring something of a population. All right, so hopefully you filled this out already and you're not just listening to me and copying everything down. Hopefully you're using your brains and thinking. But let's go through it anyways. So remember, this was our equation for a z-score. This was from back in Chapter 2. When we wanted to find probabilities using the normal distribution, some of you would find the z-score and use the chart. That's the first way I showed you. We could also use the normal CDF command. From Chapter 7, we had these equations. So we talked about the sampling distribution in Chapter 7. So the mean of x bar is equal to mu. Standard deviation of x bar is sigma over the square root of n. The mean of p hat is equal to p. The standard deviation of p hat is the square root of p times 1 minus p over n. We had some normal conditions also back in Chapter 7. When we were talking about p hat, we checked n times p being greater than or equal to 10, and n times 1 minus p being greater than or equal to 10. For x bar, either our population is normal, we could use the central limit theorem, or we can use the t-distribution as we saw back in Chapter 8 to look at a graph for no strong skew or outliers. And then we had our standard deviation check as well, so we just made sure that the sample was less than 1/10 of the population to make sure that we could use those formulas up there. All right, I'm going to get a blank page here. We're going to look at this problem down here together. So it said, assume that 30% of students at a university wear contact lenses. In a random sample of 100 students, what's the probability that the sample proportion has more than 1/3 wearing contacts? So you want to find the probability that that sample, that p hat, is greater than 1/3. Okay, so some things that we know that the p is 0.3. We know our sample size is 100. That means the mean of all the p hats is also 0.3. And the standard deviation of all the p hats is the square root of 0.3 times 1 minus 0.3 over 100. Okay? I can find that number. So I can do 0.3 times 0.7 and then divide that by 100 and then take the square root of that answer. Okay? So I'm going to keep a couple decimal places right now. So there's my standard deviation of p hat. All right, then, so what we could do, so I could leave the problem like this. So I have 0.3 in the middle. 1/3 is like 0.3333333 repeating, right? So maybe it's like right here. And I want to find this area right here. Again, picture's probably not drawn to scale. So if I'm trying to find this probability, I know it's normally distributed. If I checked my normal check here, 100 times 0.3 would give me 30. 100 times 0.7 would give me 70. So both 30 and 70 are greater than or equal to 10. So I'm going to use and obviously if it's a large university, 100 students, there probably are at least 1,000 students, so my standard deviation should check as well. So again, I'm going to use normal CDF. My lower bound is 1/3. Upper bound is E99. I've got that mean, and then I have this standard deviation. Okay, so if I go here and I do 1 divided by 3, upper bound, and I do 0.3, and then I'm going to use that standard deviation I just calculated. So we get this answer. Okay. The other way we could have done it, so some of you also might remember, is that we could have found a z-score. So this is an alternative way to do this problem. So we could have said the value minus the mean divided by the standard deviation. Divided it that way. So I'm going to go, so I have 1 divided by 3 minus the mean over that standard deviation I just found. Oops, I didn't want to put that there. I'll just type it in. I like all those decimal places there. Alright, so that's my z-score. So I get a z-score here. So since I've converted this to a z-score now, keep 4 decimal places, it's like I could find the problem going this way. So my mean would be at 0 because I converted it to a z-score. I'm no longer on this scale over here. And I'd have my 0.7345 here. So then I could do my normal CDF, 0.7345, B99, but now I'm going to use 0 and 1 because I converted it. So I have that 0.7345, 0, 1, and I get 0.2313. Okay, again, it's a little bit different, but the idea here for the difference, probably if I would have not put a 5, 6 there. Yeah. Alright, so a little bit different, but again, it's just because of rounding. But the idea here is that I could also get the answer, if you recall, by converting it to a z-score and then using the normal CDF. These are the ideas that we're going to use today when we do our significance testing. We're going to be finding that z-score. We're going to call it something different today. We'll call it a test statistic. And then we'll be finding the probability of getting that value, and this probability we're going to call it the p-value. Okay, so it's not too new, just some different ways of doing things. Alright, so like I said, we're going to continue our journey into statistical inference. We're going to learn about significance tests, specifically tests for one sample proportions and one sample means. We're going to continue to use that 4-step process so that state plan do conclude. We'll continue to see the t-distribution in this chapter, and we'll continue to use our knowledge of probability to determine if something occurring should be considered unusual. Okay? Alright, so let's now look at this significance test introduction. Alright, this one here, I want to do this with you. So if you look at this one right here, we've got two different examples. These are totally made up examples, alright? They're not real. That I'm going to help you with the basis of a hypothesis test or significance test. There are 2 different companies here claiming that they can help couples trying to have a baby girl. So this first company, Girls R Us, they claim that by taking a special pill every day for a month, it'll significantly increase a couple's chances of having a baby girl. So they take a random sample of 100 couples, and they give them this pill, and 55 had baby girls. So we get a p-hat in this sample of 0.55. Girls Rock claims that by taking their special pill every day for a month, it'll significantly increase the couple's chance of having a baby girl. So again, they get a random sample of 100 couples, and using the Girls Rock pill, 88 had baby girls. So we get a p-hat of 0.88. So just looking at this information here, so without using any statistics, I mean, it's pretty plain to see here. We got a pretty significant difference here. So based solely on just this data here, do you think that either company significantly increases a woman's chance of having a baby girl? So yes, definitely it appears the Girls Rock pill is better. Okay, obviously, like just looking at these numbers, 0.88 definitely seems higher than 0.55. So once again, Babies R Us, Toys R Us went out of business. It looks like Girls R Us will also go out of business. Alright, so this is all nice and dandy that we can just kind of look at those numbers, but sometimes it's not so clear. And so what we want to do is we want to use the knowledge that we've gained so far to try to figure out, is this result unusual or is this result unlikely? So we can conduct what we call a significance test. I'll go over a lot of this detail in the notes, but when we start off, we have a HO and an HA. So we have a null hypothesis and an alternative hypothesis. In this case, we're talking about a proportion. So I would define P as the true proportion of couples having a baby girl. Now, normally we won't do them side by side like this, that would have like one separate example, but I wanted to show you these two side by side. And right now, this first step here, my state step, my hypothesis test, is going to be the same for both of them, so I figure we'll only just write it once. P is 0.5, P is greater than 0.5 because they're saying that they're going to increase the couple's chances of having a baby girl. All right, and sometimes we have to give ourselves a cutoff. Again, we'll talk about this as we go through the notes. So we have our null hypothesis, which is just our status quo. This is what we're trying to find evidence for this one. And our second step, we call that the plan step. So we're doing a one sample z-test for proportions. This looks similar to what we did in chapter 8. Random, so yes, it says it's random. We have our normal check. Again, we just kind of re-establish that on that review, quick review sheet. When you're doing these checks, you're going back. We state in the HO that P is equal to 0.5, so we're going to use that 0.5 there, okay? So those are both met. Again, that just allows me to use my normal distribution. And then I'm assuming there's at least 1,000 companies using the stated company's pill. All right, so this is where we're going to kind of recalculate that z-score like we just did. So I'm going to take the statistic. So in this case, the statistic, I'm talking about p hat. So I'm going to take the 0.55 minus the parameter. So the population value, I believe it's 0.5, divided by the standard deviation of the statistic. Okay, well, we just talked about how we said that the standard deviation was the square root of p times 1 minus p over n. So here I'm going to take my p, I'm using p here, not p hat, like we did last chapter, over 100. All right, when you do this math, you end up getting 1. So essentially what I've calculated is a z-score. But in this chapter, we're calling it a test statistic. So is 1 an unusual z-score? Not really, right? All right, let's do the same thing over here. So I'm going to have 0.88 minus 0.5 all over 0.5, 1 minus 0.5 over 100. I do that, you do this math, you get 7.6. Again, another z-score. Is that unusual? Yeah, we've already talked about how most things are within 3 standard deviations when we're dealing with a normal distribution, so this is pretty unusual. But to take it a step further, we'll calculate that probability, or again, we're calling it a p-value here. So in this one right here, so if this would be 0, remember I converted to a z-score, so this is 0. Let's say this is 1. All right, I can't just find just the probability being equal to 1. I look on my HA. My HA is going to the right, so I want to find the probability of being 1 or higher. Again, I convert it to a z-score, so I've got that 0 and 1 there. We plug all this in, you get 1.59. So it happens about 16% of the time, this number. So what's this saying here? So just to kind of think about here, this p-value here. So there is a 0.159 chance of obtaining a sample proportion. So again, that's that p hat of 0.55 if the true proportion were 0.5. So if p was really 0.5. So, I mean, it's pretty likely that I will see this value if p is 0.5. So since it's so likely, I'll say that in this conclusion step, and again, we'll go over this in more detail in the notes. The p-value is greater than alpha. Sometimes I compare the numbers, so 0.159. So alpha, again, that's the significance level. It'll also be in the notes, is greater than 0.5. So if it's greater, I fail to reject HO. There is not enough evidence to conclude that the Girls R Us pill increases the proportion of baby girls born. Again, the likelihood of me seeing that 0.55 is high enough for me to not consider 0.55 as being unusual. On the other hand, if I come over here and if I have, again, I converted this to a z-score, Here's 0. That 7.6 is way out here, and I'm still finding the area in the right tail because remember I said I wanted to be that value or higher. So I do this one with the calculator. And I end up with 1.49 times 10 to the negative, I think it's 14th. Yes. All right, so that is extremely tiny. So again, if you think about what I wrote down here, and if we wrote it for this problem, we would be saying something like this. Again, we call this the p-value, which is the probability of getting that. So again, here I'd say there is a 1.49 times 10 to the negative 14th chance of obtaining a sample proportion of 0.88 if the true proportion were 0.5. All right, so it's not likely for me to see 0.88 if the actual value were 0.5. So since it's so unlikely for me to see that value, the true proportion probably is not 0.5. So here I'd say the p-value is greater than alpha. So again, I have that 1.49 times 10 to the negative 14th is greater than alpha. So since it's so much bigger, I would reject HO. So I throw out this idea here because it's so unlikely that I've observed that value if this were true. And I would say there is enough evidence to conclude the girls' rock pill increases the proportion of baby girls born. All right, so you might look at this and say, well, that's wonderful, but I already knew that because 0.88 is so much higher than 0.55. Yeah, you're right, but maybe sometimes it's not so clear. So maybe this number isn't 0.88. Maybe this number is 0.6 or 0.65. Is that considered unusual? So when we calculate that test statistic, it gives us an idea how far away are we from the mean, in either direction, of course, and then we can calculate the probability. And oftentimes, so we compare it to some sort of cutoff. How do we decide if something's unusual? So if we're less than that cutoff, then we're going to say it's unusual. It's not likely to happen. It could happen. It's just not likely. Since it's not likely to happen, this probably isn't true. So I'm going to conclude that this is true. All right, so that's the general idea. Like I said, I'll reference this again, but we're going to go over all these terms in the notes.